Welcome to a lesson with Dr. Powell. Let's take a look at a few examples where we can take a universal property that defines a functor and turn it into a universal property that shows adjointness. Now, this is a very nice, quick way of showing adjointness often, where a diagram like this comes quickly from a diagram like this, instead of showing a Hom set bijection where there's a lot of naturality and commutativity to pass through. But we that comes along for free and tags along. So let's take a look at the schematic here for this case when we're taking the product of two objects in a category. Okay, so we have this nice universal diagram where um, where we have A cross B, and we have projection maps to A and B, such that if we have any other object in the category and maps like this and this, there's a unique G that goes from X to A cross B that makes everything commute. Well, this diagram can easily be turned into something that has a composition of two functors as here. If we just kind of think about what's happening, see these two maps, F1 and F2, let's just double them up and double up X here to think about it individually. Like in the first component, the map from X to A, think of it as F1. In the second component, from X to B, think of it as F2. Okay, now, what about this? Do something similar to have a map from first component as projection A, second component as projection B. Now, this is the only map that's kind of left out. Well, we just kind of double it up, and pretty much it's the same description of the exact same diagram, but just shown in a little different way. Okay, so what we've shown then is we have a diagram like this, which is equivalent to this, which gives us a map to um, A comma B that is uh, uh, that is final in some sense. So if you have another map like this to A comma B, you have a unique one coming right here. And what is this delta here? That's the doubling up mechanism from the category from this category to ordered pairs of the category. We call it the diagonal functor here, okay, in this particular description. All right, so that's, and that actually gives us the same. There's equivalence, which shows us that a universal property in such a way that shows that finality is equivalent to having a Hom set bijection with naturality in this case, where the diagonal functor would be left adjoint, and pi, which would be like the product of two objects, A and B, would be right adjoint. Taking a look at that, that's exactly what's happening here. So pi of AB was how I was describing A cross B. Okay, so then we know that um, in that particular case, we have that the product is right adjoint and delta right here is left adjoint um, in this finality that we have going on right here. And this guy right here is called the co-unit of the adjunction, kind of like a final universal morphism in some sense. And then right here you have, this is equivalent through our equivalences actually to another diagram like this. Of course, this diagram that shows adjointness doesn't come directly per se from this one as much as this one does, right? But through the equivalences, it can come out. And then there is a map called the unit of the adjunction right here in this universal property. The benefit of knowing the unit and the co-unit of the adjunction is it actually gives you the bijection between this. For instance, I mean, if we had known the unit of the adjunction, we have a map in here, we send it, so this is between pairs of objects, send it to the product functor of that function. So you have an functor between two different objects, and then pull it back to x via this unit of the adjunction. So it pulls it all the way back to x, and then you get a map here. And that's actually the bijection. Then you can go back the other way using our co-unit of the adjunction. Now, what was the co-unit of the adjunction? It was simply this map, right? It was that guy, just the projection, component projection in each component. Okay, and you could see that right here. All right, so that was an example with the product of two objects in a category. Let's look at a couple other examples. So abelianization of a group. So X quotiented by its commutator subgroup. All right, and let's denote that with the functor G. So from groups to abelian groups. All right. So anytime you have a map from X to an abelian group, it factors through the abelianization uniquely. All right. So this actually shows us some adjointness happening right here. We what we can do is, well, what's F? F is the forgetful functor, where we just pretend that things we don't are just groups, and we don't kind of bat an eye about it being abelian anymore in that sense. Notice that you right here you have a morphism between abelian groups, and the forgetful functor would be ignoring that fact. It's just a homomorphism. Abelian group homomorphisms are just homomorphisms of groups anyhow. This is a very natural step to take as we're looking at this in terms of coming up with the commutative diagram. Having a forgetful functor is common. There's many examples that doing that, and you quickly get a sense and a feel for something that is as something that is adjoint. In this case, the abelianization. Notice how we have this abelianization here, this going from here to here. G would be left adjoint, and then the forgetful functor would be right adjoint. Taking a look there, maybe just reminding ourselves of the other example. So here, so we had a diagram kind of like this, but the forgetful functor was happening right here, and then the abelianization functor was happening right here. So, and notice how pi was right here, and delta was over here in that description. Okay, then we come over here to tensor products. Okay, so we have the universal property that defines a tensor product. We have A cross X, and we have a bilinear, and we look at bilinear maps from A cross X. There's a unique object such that all such bilinear maps will factor through it, called the tensor product. Here we're looking at maybe tensor product of R modules, say. Okay, now what we have here is we have some equivalences. Think about what it means to have a bilinear map from here to here. That means it's linear in each component. So if you fix something in one component, then you naturally have a linear map going from the other component into the object. That's what it means to be bilinear. That's just the definition of bilinear. Well, that actually gives us a map from, if you fix an element in X, you take an element X, you automatically get a linear map from A to Y. Done. All right. So naturally we have this, and that same idea gives you this map, because this is your, it's the same thing. This is just replacing Y. Notice that. So you naturally go from here very quickly to a diagram that looks like this. So very quickly we can see that we have adjointness happening for the tensor product with this particular Hom functor, where the tensor product itself is going to be left adjoint, and the Hom functor is going to be right adjoint. And that concludes the description of just a few examples of taking a universal property that defines a functor and turning it into something that we can easily see a jointness and say that a functor is a left or right adjoint. Thank you for watching.